Okay, back for the final part of Chapter 15 lecture, Part 5. So we need to have a way to predict the direction of a reaction. And so what we use is a comparison between Kc and Q. And Q is considered the reaction quotient, Quotient. That's what it's called. So Q is really at some point in the reaction, any random point while the reaction is trying to achieve equilibrium. And Kc, of course, is the equilibrium constant. So what we do is we calculate Q at this random point in the reaction. I'm going to give you an example of it in just a minute. And then we compare it to K. So if Q is less than K, the product concentration is too low and the reaction proceeds to the right toward the products. And if Q is greater than K, the product concentration is too high, and according to Le Chatelier's principle, the reaction will proceed to the left. And they talked a lot about Le Chatelier's principle in the videos for the lab. So if Q is equal to K, then you are right at equilibrium. So those are the three conditions that you want to be able to look for. So let's just say that this is a very simple, straightforward example where I have these values for the concentrations of two products, two reactants, and I get a value of 8. So let's say I plug in some other random values for my two products and my two reactants, and I get a value of 10. Well, now I know that Q is greater than K. So if Q is greater than K, what it means is that the products are too high. This value here, this numerator, compared to this numerator, is too high, and or the reactants are too low. And so what that's going to do, it's going to force the reaction to progress towards the left, toward the reactant side. So then what we say, in order to achieve equilibrium, if Q is greater than K, I need to shift the reaction, or the reaction will shift towards the reactants to the left. So let's go through a quick example of this. So here's a reaction where I have hydrogen reacting with iodine, producing 2HI. And so what direction must the reaction proceed to reach equilibrium? That's what I'm trying to figure out. If I know my Kc value, that's my equilibrium constant, is 50.5. So let's say that my random point in the reaction has these concentrations, or these mole values per 2 liters. And I took an extra step here. So since we want molarity, I'm going to have to divide the moles by the liters. So if I divide that by 2, I get 1 times 10 to the negative second. I did the same thing here. I divided the number of moles given. I just wanted to make sure you didn't forget about that little trick of watching in case it's not 1 liter. So I have the molarity at this random point in the reaction. So now I solve for the QC. I want to solve for the reaction quotient. So I'm going to plug right into the same expression that I would normally use, but I'm going to plug these values in that are given. And so I put them in with the 2 squared, right? So that 2 squared here comes from the 2 there. And then I don't have any power for these. So I plug in those values, I get a value of 1.33. So what I see in this example is that Q is much less than my Kc value. So what that means is that the reactants are too high and the products are too low. So if that's the case, if the reactants are too high, then the reaction will shift to the product side in order to achieve equilibrium. And so if we look back up here at this little list I have for criteria, if Q is less than K, product concentration is too low, and your reaction will proceed to the right. Whereas in the other example, I said that it would proceed to the left. Okay, and then one last thing here. This is just how to calculate equilibrium concentrations given a Kc value. So this is the same exact reaction that we just talked about. But now I'm giving you some initial concentrations. So this is an example where I would use my ice chart. And this is a little bit more complicated than the other examples that we did. So I start out with my initial amount of my two reactants. I start out with no product, which should make some sense. And then I know that this is going to go down by x. So at equilibrium, this is 1 minus x. This is also 1 minus x. And this is going to be 2x. And then I'm going to put these variables into the expression and then use my algebra to solve for x. And then once I solve for x here, right, if I solve for my x, then I'm going to use that x here and here and here to calculate my equilibrium concentration for that. And then I did that example down here. I talked about it in terms of what if you started out with 1 of the hydrogen and 2 of the iodine. Things get a little tricky. That's when you have to use the quadratic. But I'm thinking due to saving us a little bit of time, we'll, especially on a test, I'll avoid examples that use the quadratic. So that's a nice break for you. But anyway, the ones up here, this type, where you should be able to solve using square root to solve for x, that's certainly fair game. So I'm going to stop.